Now I want to show you an example that connects differential equations in terms of equilibrium points and analyzing a nonlinear system to finding critical points and extreme values or optimal values of surfaces in multivariable calculus. And that relationship requires on us finding an analog 3D surface, or a 3D analog surface. Now, not every differential equation system has a 3D surface that connects to it. This is actually a special condition that we can connect those two together. But let's look at an example that connects those two to see how we can relate some of the ideas from calculus to differential equations. First, we have a surface z is equal to a function of x and y, where we have some quadratic terms and a quartic term and a constant. To find critical points, we set z sub x equal to 0 and z sub y equal to 0. So let's take those partials. The x partial only has one term out of it, 4x. Setting that to 0 means that x has to equal 0. The y partial is z, 0 there, gives us two terms. 4y minus 4y cubed. And we set that equal to 0. This one has a few more points, so let's factor it first. I can factor out a 4, I can factor out a y, leaving me with 1 minus y squared equals 0. Now, since the cubic, we're looking for three different roots. We found 1, y equals 0, and then there are 2 right here. Y equals positive 1, squares to 1, and y equals negative 1, squares to 1, cancels. So y equals 0, minus 1, and positive 1. Now, to satisfy both of these conditions, we need to match one condition up here, x equals 0, with one of those conditions down in the bottom, the second 0 value. Now, these line up really well. There's no conflict between x being 0 and y being any of these values. So we get three critical points, which are the same as the equilibrium points we just found. Zero, 0, 0, minus 1, 0, positive 1. Okay, so now we're going to look at the second derivative test, which relates, which evaluates a determinant of second order partial derivatives of our z at these specific points. So before we go on, let me just note that as part of our analog between the surface and the differential equation, let me call this z sub x my f of x and y, and my z sub y my g of x and y. It only happens to have y and x's there, but that's the analog between the two. Then I need xx, which is 4. This would be the same thing as the x partial of f. I also need xy, which is 0. There's no y's here. This is the same thing as f sub y. And alongside that, I also need z sub yx, which will, for continuous, for differentiable surfaces, this will be the same. Z sub xy and z sub yx will be the same, giving us the x partial of our 4y minus 4y cubed. But there's no x's there, so that's 0. Well, in terms of our differential equation, this is the same thing as taking the x partial of our g function, our g slope function. And that's one of the conditions on having an analog surface, is that your f sub y and g sub x must be equal if they relate to some combined partials, mixed partials of your surface. And then z sub y, we take one more partial derivative, giving us a 4 minus 12y squared. And that will be our g sub y. Then to test these critical points, we form what in calculus is called the discriminant. D is also a determinant. And this discriminant tells us whether the concavities, these two, x or y, agree or disagree. If the determinant is positive, they agree. If it's negative, they disagree. If they disagree, they're settled. If they agree, then they're either a local min, and then the surface moves up from there, or local max, and the surface moves down from there. So let's check the d value at these 3 points. Now before we do so, let me just compare what we have here with the Jacobian. The first main difference between this discriminant and the Jacobian is that the Jacobian is a matrix. We can take the determinant of that matrix, that's true, but it starts out as a matrix. Sometimes the Jacobian is used as a determinant if we need a number or a scalar, like if we're transforming variables. But we'll keep it as a matrix right now. So Jacobian gives us x partial of f, y partial of f, x partial of g, y partial of g. And again, our f is referring to the x partial, g refers to the y partial, which means f sub x is really z sub xx, g sub y is really z sub yy, and then these two, f sub y and g sub x, are the mixed partials, which must be equal if there's an analog surface to our differential system. Okay, so when we compute the discriminant, we're going to get something that's very similar to the Jacobian we just got. So there's our Jacobian matrix. The determinant of that matrix is positive. In terms of multivariable calculus or second derivative test, this means that the two concavities agree. Well, that's pretty obvious. They're both 4. And what do they agree on? Well, they both agree that they have positive concavity, which means the umbrella is opened up and we have a local min. The discriminant at the two other points is the same, because plus or minus 1 squared here will give us the same value. And so we have the determinant of 4, 0, 0, negative 8, giving us a negative 32, negative. And since the concavities disagree, we have a saddle at these 2 points. And a saddle, in terms of the second derivative test, is a point where it looks like a local min in one direction, but looks like a local max along another direction. You can think of that as a saddle, or a mountain pass, or a Pringle chip kind of shape. Okay, so now let's connect this back full circle to the phase plane for a differential system. The origin, 0, 0, was described as a source or a duplicate source in terms of our differential equations, our trace determinant plane analysis. But in terms of the second derivative test, we call it a local min. Well, what's the difference? Well, a local min is a point where the surface goes up as we go out. And the arrows we're drawing here are the gradient, or directions of greatest increase. So the gradient directions will tell us which way to go up. Well, it turns out that if it's a local min, every direction is up. And the greatest directions actually are a balance of those four, since we have the same eigenvalues in each one. Every combination of those two is the greatest direction going up, because they're all equal. So we have essentially a little bowl right here, and then as we exit that bowl as we exit the bottom of that bowl, we're going up and up. There are two directions where we hit a maximum, a local max along a slice. So we go up, we hit a point where it'll then go down again. Now, the arrows tell us where to go to increase along the surface. So when you have two arrows both pointing at a point, that means those are two lines where you're increasing to get to what looks like a local max in that direction. But it's a saddle, which means that it's only a local max along a certain edge. And then it moves upward again from there. And so we have our local min moving up, 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 and then moving up, up, up again. There's our saddle, local min. The same thing happens on the bottom. So let's take a look at this type of behavior as a 3D object. So here we go. I've opened up both p-plane on the right-hand side and Wolfram Alpha for this surface on the left-hand side. And you can kind of see a little bit here. We have the ribbed edges where the saddle, one of the saddles is. On the other side is the other saddle. And right in between is a little pocket where you have the local min. Down below is a contour plot that shows you the different levels of that surface. The lowest level on the interior is where that local min is, right in the center here. And then we have a cross on the level sets. That's where the saddle is. See that it's low, coming up to a high point, and then back low again, if you're following along that stable manifold. And then we go up, up, up to the right, or left, up, up, up to the right, and that's the unstable eigenvectors. The same thing goes down below. Unstable to the left and right along the x direction, stable coming up to a point along the y direction. And now if we fill out some of these solution curves, these again, if you compare a differential equation system or solution to a surface, the curves are the directions of moving up along that surface, following the gradient, essentially. And you can see the closer and closer we are to the stable manifold along the y-axis, the tighter we are, closer we are to getting, whoa, there it is, getting to that equilibrium point that is a saddle. Does have some stable curves to it. I hope you also enjoy watching the other demo video where Dr. Mitchell shows the comparison between points traveling along a surface and moving along the phase plane itself. So watch that demo as well.